All right, today we are in Chapter 10, Section 1, and we're going to be looking at sequences as functions. So the first thing we're going to start off with is a key concept, and it says that a sequence is a function in which the domain consists of natural numbers and the range consists of real numbers. So if you don't remember what these terms mean, a natural number are the positive whole numbers. So it starts with 1, 2, 3, etc. Up to some number. That's what the domain shows right here. And the range can be any real number. So it can be a positive number, a negative number, 0, decimals, fractions, anything. But the domain is always a positive whole number. So you see here we have an example of a sequence 3, 6, 9, 12, 15. That's a finite sequence because there's only 5 terms in it. And we also have infinite, or the opposite of finite sequences, which says 3, 6, 9, 12, 15, and then ... means it keeps going forever. So first example here, we need to determine whether the sequence is arithmetic. So the concept here of arithmetic is, does it have the same number that you add or subtract to get the next number in the pattern each time? And so our terms are -3, -8, -13, and -23. And what you should be able to see from this is that if you find a common difference, you're looking for the amount that it changes by every time. From -3 to -8, it's -5. You go down 5, then you go down 5 again, but then you go down 10. Which means there is not a common difference, and because there is not a common difference, that means that the sequence is not arithmetic. For part B, we have the pattern -8, -2, 4, and 10. So again, we're going to look for a common difference. Do we add, do we subtract the same number every time? And this time you can see that we add 6 every time to get the next number in the pattern. There is a common difference of 6, which means that this sequence is arithmetic. Got a couple of check your progress problems. Just pause the video and work through this, see if you can get your answer. The answer to this one is B. There is a common difference of 11. And looking at part B for check your progress, we have another pattern 22, 14, 6, and 2. And this time we see that there is not a common difference. From 22 to 14 is 8, 14 to 6 is 8, but from 6 to 2 is only 4. So this is not arithmetic. Example 2, graphing arithmetic sequences. Part A says we need to consider the arithmetic sequence -8, -6, -4, and then find the next 4 terms in the sequence. So when you're given a pattern like this, the first thing that you want to do is to figure out what the common difference is. So you can write the terms out, the way they've been written, and just say, how do I get from -8 to -6? How do I get from -6 to -4? That's one way to look at it. The other way you can look at it is what they say here, which is taking any term and subtracting the term that comes before it. So if you did -6 minus -8, or if you did -4 minus -6, every time you'd get 2. Or if you just went -8 to -6, oh, I have to add 2. -6 to -4, oh, I have to add 2. Either way works for finding out the common difference. And then if you just want to find the next 4 terms, you just write your pattern out and you add 2, you add 2, you add 2, you add 2, etc. It's really basic. So for this sequence, of course, our next 4 terms would be -2, 0, 2, and 4. Part B, we're now going to graph the terms that we found in part A. And so the way you graph this, the domain consists of the term number. So the first term is -8, and the range is the actual terms itself. So these just generate coordinate pairs. So we're going to graph the coordinate pair 1, -8, 2, -6, 3, -4, etc., etc. And you can see here, we've just graphed a bunch of coordinate points. And hopefully you realize that if you graph these points and you connect them, that you form a straight line. And this will be true of every arithmetic sequence. A couple check your progress problems. First one, we have an arithmetic sequence of -2, -13, -22, -13, -4. We're asked to find the next 4 terms. The answer for this one is D. And then part B, we're going to graph these terms. So I just figure out the graph, what it would be. Moving ahead, we see the answer is B. Again, they form a straight line. You'll notice that all 4 of these graphs form straight lines. It's just a matter of, did you graph the correct points? Example 3 now, we're looking at a real-world problem on the marching band. It says, during their routine, a high school marching band marches in rows. There is 1 performer in the first row, 3 performers in the next row, and 5 in the third row. This pattern continues for the rest of the rows. Use this information to determine how many performers will be in the 20th row during the routine. And so the first thing that we want to do in this kind of problem is to figure out what's the common difference in the rows. And you can see that first row has 1, second row has 3, third row has 5. The pattern is changing by 2, so there's a common difference of 2 every time. So then they want us to use point-slope form to write an equation for the sequence. And because our common difference is 2, that's kind of like your slope when you graph a line. So m is 2. And we have a coordinate point of 3, 5, meaning that the third term in the pattern was the number 5. You could also use the first term in the pattern was 1, 1, 1. You could use a second one. Second term was 3, 2, 3. Any of those points works. And then we're going to solve for when x equals 20. So using point-slope form, plugging the numbers in, we work down to the equation y equals 2x minus 1. You plug in 20 for x, and you get that there would be 39 people in the 20th row. If you wanted to check this, you says you can find the terms of the sequence by adding 2, starting with row 1 until you reach 20. This would be super tedious. So I would suggest you just make sure you're accurate with your math the first time through. Here's a check your progress problem. Go ahead and pause the video, give yourself time to read the problem and work through it. And I'm going to advance to the next slide and show the answer. And the answer for the real-world problem is C. There'll be 49 blocks in the 13th level of the pyramid. The next thing we're going to look at is a geometric sequence. And so we need to determine whether or not a sequence is geometric. And we're given the numbers 8, 20, 50, and 125. So the difference between a geometric sequence and an arithmetic sequence is that arithmetic sequences add or subtract the same number every time, and a geometric sequence multiplies or divides by the same number every time. So if you want to find the common factor for the pattern, instead of adding or subtracting the number, or instead of taking one number and subtracting the number that came before it, for geometric, you take a number and you divide by the number that came before it. So you can see here that we did 20 divided by 8, and that reduces to 5 halves. We did 50 divided by 20, and that reduces to 5 halves. We have 125 divided by 50, and that reduces to 5 halves. So each time they have the exact same ratio of 5/2. And because they have the same ratio, that means that this sequence is, in fact, a geometric sequence. Part B, we're going to look at another pattern. We've got 19, 30, 41, and 52. And when you look at this pattern, if you're going to take a number and divide by the number that came before it, you can see every time that we get a different ratio, which means that this sequence is not going to be geometric because the ratios are different every time. However, I don't think they're going to mention this. If you look at the terms, there is a common pattern every time of adding. They're adding by 11 each time. So this would have been an arithmetic sequence, but it's not a geometric sequence. We've got a couple check your progress items. Go ahead and pause the video, read through the problem, and find your answer. For this problem, the sequence is geometric. You should have found that it has a common ratio. The common ratio here would have been -2, 8 divided by -4, -16 divided by 8, etc. They all give you -2. Looking at part B, we've got another pattern. Go ahead and pause the video, work through the problem. And you will see that the answer for this one is that it is not geometric. You get a different ratio each time when you divide numbers by the preceding number. Now, example 5, we're going to be graphing geometric sequences. So we have the geometric sequence 10, 15, and 22.5, and we're going to first find the next 3 terms of the sequence. So in order to do that, again, we're going to take any number and divide by the number that came before it. So 15 divided by 10, or 22.5 divided by 15. When you do that, you're going to get a common ratio of 3/2. So once you figure out that common ratio, you're going to take the last number that you're given, 22.5, and multiply it by 3/2. And you're going to continue doing that each time to get the next terms in the sequence. And when you do that, you will find that the next 3 terms are 33.75, etc., etc. You can read that on your own. Part B of the problem, and we're now going to graph the first 6 terms that we just generated for this sequence. So again, the domain are the term numbers. So the first term was 10, the second term was 15, etc. The last term, 6, was 75.938. When we graph these, you will see that we do not have a straight line, but it forms a curved pattern. And in a couple more lessons after this, we'll eventually figure out what this is called when you have this kind of a curved pattern. But for right now, you don't technically know what that pattern is, what the graph of that is. So checking our progress, go ahead and pause the video, read through the problem, and figure out the next 3 terms for the sequence. And we can see this time the answer is D. For part B, we're now going to graph those 6 terms. Remember that you're looking for a curved pattern. And the answer for part B is choice A. We're going to go ahead and pause the video right here and pick up with example 6 in the next video.